So let's prove conservation of linear momentum using Newton's third law. For that, we are considering two objects A and B with mass m1 and m2 moving along the same direction and along a straight line. So by default, it has to be the straight line with the velocity of u1 and u2 respectively. So here, say the first object has more velocity than second object, and this leads to collision. After the collision, we have the velocity of v1 and v2. Quite simple. So we have three different cases. This is before the collision. So we have two objects of different masses. The velocity this has is much more than this. Okay. So u1 is greater than u2. And we'll call this as A and B. And this is m1 and m2. This is during collision. This is before collision. This is during collision. When it collides, what happens? I need to copy this too. Yeah. So this is the most important part. If you can answer this, you're done. When they do collide, what happens? Yes, force are exerted. This is force on B by A, and this is force on A by B. This is during, this is before, and next we have the after. I think you guys are a bit off of the screen. That's better. Then this is after. So obviously we have the objects moving apart, but with different velocity. Or let me copy this itself. Say after the collision. So this is a small v and this is a larger velocity. So this is v1 and this is v2. Okay, guys, commonsensical, right? All of this is quite commonsensical. So I'm going to write a generic statement now. Okay, so something called as impulse approximation. This you guys can use in quite a few places. So we assume that collision will take place so fast that any other external force cannot significantly alter the momentum of the particle, of the participants or the particle or the objects, whatever you guys want to call it as, during the time delta t. So what we are trying to tell is all the things that happens within this short duration, anything else other than this two interaction, any other force acting on it is to be ignored. Okay, so everything and anything during this time period should be ignored other than these two forces, right? So this is basically, this implies your external force is equal to 0. Simple, that's it. And since the external force is 0, the system is, for this moment of time, isolated. Now, next step is that from Newton's third law, what can we tell? FAB should be equal to FBA, but when we take into account the direction, it is negative. Multiplying delta T both sides. What we have here is delta T FAB is equal to delta T minus FBA. Okay. So, but force is equal to mass into acceleration, right? Or we can also go with what else? Force into time. What else will it give? What does it give? Force into force into time will give us, yeah, correct, change in momentum. Okay. So basically you have m1, the initial momentum, final momentum minus the initial momentum should be equal to minus of final momentum minus the initial momentum. So this is the picture. A bit of rearrangement and we have m1 v1, and if this goes to the right hand side, m2 v2, negative of negative is positive, m2 u2 plus m1 u1. So what is this? This is nothing but your final momentum. The system is made up of two particles, and this is equal to initial momentum of the system. Okay, so that you guys can write, and that's how you get to prove it. Okay, so what did we see? We saw two objects colliding and their velocity is changing, right? This is happening here throughout. So we used this very animated video to explain the idea of conservation of, or introduced the idea of conservation of momentum, linear momentum, right? And but there is so much of interaction. How can we tell that the momentum is same? We just saw that. We just saw each of the collision that's happening over here can be justified with this. This is one dimension. You can change it to two dimension. Of course, it's more complex, but point is you can extend it. Extend the idea. So when it collides, if there is any other external force acting on it by chance, say gravity and all of that, even that can be ignored during the collision. And when we use this particular, basically this result or this law, obviously these two are equal but opposite in direction. And when we multiply delta t, because that's the time of interaction, and we know that force into delta t or force into time itself is the same thing, will be equal to delta p, change in momentum. This is again from your Newton's law, second law, and bit of rearrangement and you have your final answer. Okay, so you guys can write this part. You need to introduce the diagram, and we'll jump on to this.